Welcome back. In this session, we'll see the meaning of what is the meaning of P, which is we defined in the previous session as real power, and Q, which we defined in the previous session as the reactive power for RLN. See, what do we mean by this? So let's take the first element, that is the resistor. So if we have a resistor, right? So we'll say we are given simply the voltage across the element is Vrms. So this time we'll consider the RMS values. So we are given the voltage and currents in terms of RMS values. Now you can take the maximum values, peak values as well. So there is nothing to do. Only thing is, then the definition of, you have to use a different definition of Q and P. All right. So how do we define P when Vrms and IRMS are given? So we know from the previous session, P we defined as Vrms, IRMS multiplied by the cosine of the angle, that is theta V minus theta I. Okay, cosine of the angle minus the phase difference, which is the phase difference between voltage and current. Okay, so this is how we define. Now we know what is the phase difference of the voltage and current in the resistor. We know theta V is equal to theta I. So there is no phase difference as far as this resistor is concerned. So in other words, in resistance or in resistor, the voltage and currents are in phase. So what is theta V minus theta I? That's equal to 0. That means theta V minus theta I is simply 0. So substituting the value, what we'll get? So we'll get P as Vrms IRMS multiplied by cosine of 0, because theta V minus theta I is 0. So this is simply, and cosine of 0 is 1. So we'll get Vrms IRMS times 1. So that means the power, the real power in resistor is simply given by the multiplication of RMS values of the current and voltage. So this is how we define the real power or the average power absorbed by this, and this is referred as the power absorbed by this resistor. So this is the power absorbed or consumed by this resistor. All right. So P is equal to Vrms IRMS. Okay. So this is how we define the power. All right. Now if we say Vrms is equal to R times IRMS, right? From the Ohm's law. So if you remember Ohm's law, voltage is equal to current multiplied by the resistance. So if we substitute these quantities, so we can get another for equation for this power, average power. So it is Vrms times, if I substitute the current in terms of this voltage, so it will be Vrms divided by R. So you can write it as Vrms square divided by R. R, if you substitute the value of Vrms in terms of resistance and current, you can get another equation of this. So you will get, instead of Vrms, you will write R times IRMS. And we have IRMS here, so it will be IRMS, that will be equal to I RMS square multiplied by. So this is how we define the power in terms of the RMS value. Right now, if we substitute the value of Vrms and IRMS in these quantities, you can also define this average power in terms of peak value. So when you put Vrms is simply Vm divided by under root of 2. So Vrms in terms of maximum value or the peak value is simply Vm divided by under root 2. So if you substitute it back here, what we'll get? We'll get simply Vm square divided by 2R. And if we put value of the IRMS simply Im divided by root 2. So we will get Im square divided by 2R. Okay. So these are the expressions in terms of RMS values, and these are the expressions in terms of the maximum values, where IRMS is simply Vm divided by under root. So this is how we define the average power. of a resistor. And this is referred as the power absorbed by the resistor. Simply, this is called the power absorbed or power consumed by the resistor. So this is the power absorbed or consumed by the resistor. So this is the power absorbed. So if you know the voltage and currents, you can use this expression. These expressions here, VRMS, IRMS. But if you know only the voltage in terms of RMS or peak value across this element or R, you can use this expression. Okay, so this is the power consumed by this resistor, and its unit is watts. So the unit is watts, W. Okay, so this is how we define the average power consumed by the resistor. Now, how do we define the reactive power? So reactive power, if you remember from the previous session of, so what is the definition of reactive power first of all? So reactive power is denoted by the capital letter Q, and it is given by VRMS, IRMS times sine theta V minus theta. Okay, so what is the phase difference between voltage and current? You can see the phase differences. So putting the value of theta V minus theta I equal to 0, sine of 0 is 0. That means Q for a resistor is 0. This is very, very important. So now, what is the meaning, physical significance or meaning of Q? It means the power absorbed by the passive element, or power, sorry, it means the power stored by the passive element. So Q means the power stored by element. So the element under consideration is R. So it means the power stored by the resistor is equal to 0. As we know, resistor only consumes power, it does not store power. Okay, so Q for a resistor is 0, because as we know, the power stored by this resistor is 0. Okay, in other words, what is the takeaway from this? So we can say simply, so if we know this, resistor does not store power. So in short, we can say a resistor does not store power. So Q is 0 for resistor. It consumes power. Resistor consumes power, and it is denoted by P. And you can use P as either VRMS. Let me use capital letters. So we can say P is VRMS square by or IRMS square times R. There are different expressions that are given above. Okay, so it only consumes power, and how much is the power consumed by the resistor? Voltage, RMS value of the voltage square divided by or RMS square of the current multiplied by R. Okay, so this is the power stored or consumed by this resistor. Okay, now next element is inductor. So if we have inductor, how do we define P and Q for inductor, right? If we know the voltage and currents across inductor, so let's be so you know, in phasor domain, what we do to the resistor, we replace it by j omega L or simply jx, where x is omega L. So this is the impedance offered by the inductor to the flow of current. So if I say the voltage across this is VRMS, and the current flowing through this element will be IR. So again, since we are given impedance of this element, we can use the Ohm's law. So Ohm's law is simply V is equal to I times Z. Now this time the voltage and currents are in terms of RMS values. So if we substitute the VRMS will be equal to IRMS times JX, where X is omega L. So you can write it as IRMS times X, J. J can be written as at an angle of 90 degrees. So what is this expression saying? Simply that the voltage is ahead of current by 90 degrees. That's the meaning of this statement here. So this statement means simply voltage phasor is ahead of current phasor by 90 degree. In other words, what's the meaning of this? That means theta V is actually equal to theta I plus 90 degree. In other words, what does it mean? Theta V minus theta I is 90 degrees. So the phase difference between voltage and current in this inductor is 90 degree plus 90 degree. So voltage phasor leads the current phasor by 90 degree. Or in other words, current lags the voltage by 90 degree. Usually we talk in terms of current. So current lags the voltage by 90 degree. That's the meaning of this sentence. Current lags the voltage by 90 degree. All right. So from this, you can say theta I is simply theta V minus 90 degree. In other words, the current phasor lags the voltage phasor by 90 degree. Usually we talk in terms of current. Okay, so how do we define P? So now we know what's theta V minus theta I. How do we define P? If we know VRMS, IRMS, how we define P for this inductor? So P for an inductor, we know from the definition is VRMS, IRMS times cosine of theta V minus theta I. Now substituting the value of theta V minus theta I, what we will get from this? So we'll get VRMS, IRMS times cosine of 90 degree. What's cosine of 90 degree? Because theta V minus theta I is 90 degree. That simply means cos 90 is 0. So power absorbed by the resistor, so inductor is 0. So average power consumed by this resistor is 0. So P means the average power or the real power. Okay, P is, what is the meaning of P? In the last session, we said P is called the real or average power. So the real or average power consumed by the resistor is simply equal to 0. So P for an inductor is equal to 0. This is very, very important expression. Means P means inductor does not consume power. In other words, inductor does not consume power. Okay, that's the meaning of this sentence. Now, how do we define the reactive power for this? So if we know the average power, now how do we define the reactive power? We know the reactive power is denoted by VRMS, IRMS times sine of theta V minus theta I. So substituting the value of theta V minus theta I, what we'll get? We'll get VRMS, IRMS sine of 90 degree. How much is sine 90? Sine 90 is simply 1. So Q for an inductor is simply VRMS, IRMS. Okay, Q is simply VRMS times I. Now from this expression here, you can substitute the value of VRMS. I'm talking about the magnitude, IRMS times X. So you can substitute it, right? So you can put it here. You can say as VRMS is equal to IRMS times X. Actually, there is J also, but we are talking only about the magnitude part. So magnitude of this will be some magnitude of this RMS voltage will be equal to this. Okay, magnitude of J is simply 1. So this will be simply VRMS is simply IRMS times X times IRMS, where X is omega L. Where X is omega L. So how much is this? So this will be simply IRMS square times X. So this is one expression of Q. Also, you can replace IRMS by VRMS by X. So from this expression, if you replace IRMS by VRMS by X, so you can get another expression for this. If you know the voltage, RMS value of the voltage, you'll get VRMS times, use dot instead of X because we are using X for reactance. So it will be simply VRMS divided by X. So the expression will be simply VRMS square divided by X. Okay. So this is if we use the RMS value. Now, if we use the peak value, we know how the RMS value and peak value are related. RMS value of the current is simply Vm divided by under root 2, and RMS value of the voltage across the element is simply Vm. Sorry, this should be Im. So this is the maximum value of current. So this is Vm divided by under root 2. All right. So if we put it here, so we'll get, this will be simply Im square times R divided by 2. This will be simply Vm square. Sorry, this is not R, this is X. So X Vm square 2 divided by X. So this is how we define the currents in terms of RMS values and peak values for this inductor. Okay, so it is simply equal to the RMS value square multiplied by X. X is omega L simply, where X is simply omega L for inductor. All right. So this is referred as the reactance. So this is the reactive power. Now, what is meant by reactive power? This is the power stored by the element. So the power stored by the inductor is given by either this expression or this expression. Or you can use this expression or this expression in terms of voltage and currents. So inductor stores the power. It does not consume power. So what is the takeaway for this element? Inductor does not consume power. Does not consume power. Okay, that's the first. Inductor stores power. Stores power. Why? Because we know P is equal to 0 for inductor and Q is not equal to 0 for inductor, and Q is given by these expressions. Okay, so Q is the reactive power stored by this element, or simply the power stored by this element. Okay, and this is for this inductor. All right, now next we move. Okay, now one more statement about this, very important. If we say the current lags the voltage by 90 degrees, in inductor current lags the voltage phasor. Current phasor lags the voltage phasor by 90 degree, means if I have to draw it on the complex plane or this vector plane, we'll say if this is the voltage phasor, this should be the current phasor. You know, voltage phasor is ahead of current phasor by 90 degree. That's why inductive loads are referred as lagging loads. So if you have an inductor in the load, so inductive loads are referred as lagging loads. Inductive loads, what do I mean by inductive loads? Means where the inductance is present. Inductive loads are lagging loads, are called as lagging loads. All right, so I hope you get the meaning of this. Now, what is the example of a lagging load? For example, this motor that we use to pump the water, or electric fan that we have in our homes. Okay, so what are the examples of this? Examples of, for example, electric fan that we have at our home, ceiling fan usually. Okay, or electric motor. These are the examples of lagging loads, or in other words, inductive loads. These are referred as lagging loads. Now, what do we mean by lagging loads? That current is lagging the voltage. In these circuits, current is lagging the voltage. All right. And most important point, Q is positive. So whenever you compute S, and S is P plus JQ, if this is positive here, now you can directly consider that this is a lagging load or inductive load. Okay, so you can directly infer from that S is, since Q is positive, means the imaginary part of Q is positive. So you can directly say the circuit is inductive in nature, means it has inductance. Or in other words, the inductor is dominant. If it has capacitance as well as inductance, so you can say the inductor is dominant there. Okay, All right, so this is about inductive loops. Now let's talk about the last element, that is the capacitor. So if we have a capacitor, then let's again suppose we are given the RMS value of this voltage and currents. So we say this is VRMS, and the current flowing through is IRMS, and we are given the reactance of this capacitor. We know the reactance of this capacitor is given by 1 by j omega c. That can be written as minus j by omega c. That can be written as minus j x, where x is simply 1 by omega c. So this time x is equal to 1 by omega c. So this is the reactance offered by the capacitor. Okay, we already studied this phasor analysis in the class, so just replacing c by 1 by j omega c. All right, so if we relate the voltage and currents, we write using the Ohm's law, we write Vrms is equal to Irms times minus jx. This is the impedance, because Ohm's law says V is equal to Iz, where Z is simply minus jx. I is Irms, V is Vrms. Okay, so what is the meaning of this? This simply says this is Irms times x minus g can be written as minus 90 degrees. Minus g is simply minus 90 degree. So what is this saying? That the RMS value of the voltage, or simply the voltage phasor, is lagging the current by 90 degree. So if we say theta v is equal to theta I minus 90 degree, that's the meaning of this sentence here. Okay, so theta v is equal to theta I minus 90 degree. In other words, voltage is lagging the current by 90 degree. Or since we usually talk in terms of current, so we can say theta I is equal to theta v plus 90 degree. So what is the meaning of this statement? This statement simply says current is leading the voltage by 90 degree. So if we draw the voltage phasor and current phasor of this capacitor, means if we draw the voltage phasor and current phasor, we are now drawing the magnitude part accurately. We don't know what's the value of Vrms and what's the value of RMS, I mean the magnitude. Yeah, so you can draw the vectors accordingly. So if we say this is Vrms, or simply V phasor, let me call it V phasor, then we say this is the current phasor. Now you can see the current is leading the voltage by, it is ahead of voltage by 90 degree. You know, this angle is 90 degree. We can also draw it like this. So there is nothing wrong with this. We can say this, if this is voltage, then current will be here. Okay. Current will be here. These are one and the same things. Okay. These plots are one and the same. So they are one and the same plots. Okay. You can see only the current is ahead. Okay. So positive angle is calculated in the counterclockwise direction. You can see current is ahead by 90 degree here. Right. So this is the meaning in terms of theta. Okay, what is theta v minus theta I here? What is theta v minus theta I? From this expression, you can see it's equal to minus 90 degrees. So the phase difference between voltage and current is minus 90 degree. Okay, so this is the phase difference between voltage and current. Now, what is the definition of the real power? So if we denote the real power, we know the definition. The average power, real power is also called average power. So it is denoted by the capital letter P, and it is given by Vrms Irms times cosine of theta v minus theta I. So substituting the value of Vrms and Irms and theta v minus theta I, so we'll get Vrms Irms. Cosine of theta v minus theta I is cosine of minus 90 degree. Cosine of minus 90 degree is simply 0. So the P is equal to 0. So the power consumed by the capacitor, because P denotes the power consumed by the element, average power or the real power consumed by the element, is equal to 0. So capacitor does not consume average power or real power. In other words, capacitor does not consume power. So what is the meaning of this statement? Capacitor does not consume power. Now, how do we define the reactive power? So if above is the real power, now the reactive power is defined as by the capital letter Q, that's equal to Vrms IRMS times sine of theta v minus theta. So substituting the value of theta v minus theta I, it's equal to minus 90 degree. So it is VRMS IRMS sine of minus 90 degree. We know sine of minus 90 degree is simply minus 1. So it will be minus VRMS IRMS. Okay, so Q is simply this. So Q of a capacitor is minus this. So the power stored in the capacitor is simply minus times VRMS IRMS. All right. So Q for a capacitor is negative. Okay, so if you have to simply identify which element is it, which load is it, so you can say this is a, if the Q comes out to be negative, you can say it is a capacitor load. Okay, now if we substitute the value of VRMS, IRMS from this expression, only the magnitude. Okay, I'm talking about the magnitude. VRMS is equal to IRMS times X. What will be Q here? So Q will be simply given by, if we use VRMS is equal to IRMS times X, where X is simply given by 1 by omega C. So if we put it in this, so we'll get VRMS. Now I'm talking about the magnitude part only. Okay, we'll talk about the magnitude. So it will be VRMS divided by X. If I get the value of IRMS X here, IRMS from this, so we'll get VRMS divided by X. So this will be equal to VRMS divided by VRMS square divided by X. So this is Q. Or if I put VRMS is equal to IRMS times X here, so we'll get Q as IRMS multiplied by X times IRMS. This is the value of VRMS. So we'll get IRMS square times X. Okay. All right. So if we use the peak values of the quantities, if we say VRMS is simply VM divided by under root 2 and IRMS simply IM divided by under root 2, the RMS value in terms of peak values. So we'll get VRMS simply as, we'll get this as VM square divided by twice X. Here we'll get simply IM square divided means maximum value square divided by 2 times X. Okay, so this is the relationship of Q in terms of RMS value of peak value, and the unit is VAR. So the unit here is VAR, volt ampere reactive. This is the power stored by the capacitor. Okay, so what's the takeaway from this? So you can note it down. Capacitor does not consume power because P is 0. Capacitor does not consume power, or real power, or average power here, means P is equal to 0 for capacitor. Okay, that's the first thing. Now, second thing we'll learn, capacitor stores power. Capacitor stores power because Q is non-zero. And how do we define Q? Q is defined here in terms of voltage and current. And current leads the voltage by 90 degree. Current leads voltage in capacitor by plus 90 degree. That's why capacitive circuits are also referred as leading circuits. So that's why these circuits are also referred as leading circuits. All right, and Q for a capacitor is minus. Okay, so if the Q comes out to be negative in the calculation, you can simply say that this is a leading circuit or simply capacitive circuits. All right, so let me end this session here. In the next session, we'll solve problems based on this. All right, so let's end it here.